Welcome, everybody. This week, we're going to be working on Unit 8, which has us looking back at machine learning models and how we might apply them for natural language processing. This will reinforce a lot of the concepts that we were looking at in the previous course and how they apply here. So it's a little bit of refresher, but also a different approach in the application. This material, of course, does come from Intel Corp, and I'm borrowing their slideshow here for the material. So I'm just going to step through all the stuff here. Just a recap, last week we were talking about pipelining and NLP and the different steps, and relative to our own pipelines, and then building NLP models and splitting the data set. Our agenda for this week is basically implementing machine learning models after the data split, looking at some of the different classification models that we've looked at before, including Naïve Bayes, decision trees, and random forests. We'll review neural networks and deep learning in NLP. We'll look at language modeling, and then we'll look at reinforcement learning from human feedback. Last week, as it says here, we acquired data, we pre-processed the text data and split it into test and training sets. And now the data is basically ready to be analyzed with different ML models. Once again, here are some of the basic classification models. I added one to the list here from what we saw above. But if you recall, we looked at all of these in the previous course in detail. When we look at the Naïve Bayes classifiers, this is part of the scikit-learn library, so we can import this, and you notice the techniques for doing the imports with Python code. So they're basically indicating here that you need to call the classifier first, and the training data is obtained using the train test from the whole data set. They do have some information here, and I do encourage you to start looking at some of this scikit stuff here, because they do go in and explain how their libraries work here. And scikit-learn, being one of the more popular ones, has a really excellent documentation set. So if you get out there working professionally with this stuff, you can always use this as a reference, kind of like we use W3 Schools as a reference for Python. It's really, really helpful. They tell you what the parameters do, all the different attributes and everything. They even give you examples of how to apply it with sample data, which you can, copy the code and then tweak it to your needs. So this is really, really a helpful website. So whenever I hit those slides, I would encourage you on your own to go take a look. One of the advantages of this approach, of course, is it's easy and fast to predict the class. It performs well when we have multiple class predictions. And it says when input features are not dependent on each other's, this performs better as compared to models like logistic regression. And you don't need as much training data. So that's another advantage of this approach. There's also the decision tree classifier. Once again, there's a link here to the scikit-learn website. This is the basic implementation here with Python. Notice that we're pulling from the scikit-learn tree, and then some of the syntax that goes with it. You just basically need to call the classifier, and the training data is using the split method, once again, from the whole data set. Random forest, also from scikit-learn. Here's the Python code for that. You just basically need to call it, and once again, we're using the whole data set with a split for training and testing. Read more on it from this link here. All right, they do a little bit of comparison here, and they talk about decision trees are a lot easier to interpret and understand, basically. A random forest combines a bunch of decision trees, and it becomes more challenging to interpret. There's, basically you have more branches to follow. Also, the random forest has a higher training time than a single decision tree. So if you can, once again, break your problem down into pieces, it might be a little bit easier to process. The random forest is suitable for situations when we have really large data sets. And we're not really concerned overly with how interpretable it is. Right. They make a point here that it becomes pretty crucial to know how to pick good NLP models, like which model approach are you going to apply? Um, and, there's algorithms that can help you kind of figure out how to do that. Scikit-learn has put together kind of this map. I've kind of put this into our unit here as an extra credit assignment where I grabbed a different version of this graphic, and you can follow that link below and see the updated version. And I'm going to just make it a little bit bigger here as I'm lecturing on it. But basically what it is you have a starting point and you walk through this kind of like you would a flow chart. So think back to like Python class when we were doing flow charting of a programming problem. This is chock full of decision points. They're not using proper flow charting approaches, but whatever. You get to a decision point, and for example, you start, and if you have greater than 50 samples, you can proceed to pick a category. But if you don't, you got to get more data, right? And so they just kind of walk you through here based upon what you have, what your data looks like, and then you end up either in classification, clustering, regression, or dimensionality reduction. Generally speaking, if you're predicting category, option one, you have labeled data. You need to follow the classification approach and its algorithms. If you don't have labeled data, you end up doing clustering. Also, if you're predicting quantity, you need to go for regression. Otherwise, you go for dimensionality reduction. And then the subsequent slides here are basically what I have as an extra credit assignment for now. There's some other group activities in this slideshow too that I may turn into extra credit as well, or we might just kind of wrestle with those during class time. We'll see how the time works out. Some ways to figure out how good our models are is basically how accurate it is the ratio of the number of correct predictions to the total number of input samples. So we're looking for high accuracy. We can also look at confusion matrices, and a matrix is an output that describes the complete performance of a model as kind of like a simple table format. All right, they do have some slides here talking about this and how you actually calculate it. So when you do have a confusion matrix, you're often presented with this type of information, right? Like the predicted and no and yes columns, and then the actual no and yes, and you form a little matrix and you score them, like how often it fits into that category. And of course, up in the upper left-hand corner there is the number of samples that we're working with. The general formula for figuring out if this is correct or not, or what the value is, actually, I apologize, is this formula here, where basically you look at the true positive divided by the true positive plus the false positive, and then you get this ratio, and it gives you a score. And that will tell you the accuracy of it. Now, rather than just give you the answers, I'm going to leave these out there as an activity that we could complete. But you notice they have 4 different scenarios here with different sample sizes, different results that you can calculate. So we'll come back and look at those during actual class time. Let's move on to neural networks. They're a little bit more precise than using plain counting. And they also help get better accuracy compared to simple methods. Okay, so let's kind of do a little bit of review on this. With a neural network, we will have multiple inputs. Once again, they have a little link here that takes us to scikit-learn. I'm actually going to run out to it really quick. And they kind of have all these different things here and tell you what they're about. So I would like, if you really want to read up, this is a great website for reading up on this stuff, because not only do they talk about the libraries, but they talk about the concepts too, right? And from a working professional's kind of standpoint, which I think is why this is very useful. I'm just going to pull that off the screen for now. All right, so we have our inputs, we have our node, and then we have weights on each one of these inputs. And of course, there's an output. Notice that there's a direction of flow with the neural network. The neuron in the middle will have a non-linear activation function. W will be the input weights, and then the activation function will maximize between 0 and a particular value. With these, we also have an output that happens. So just be mindful of that. And the output is calculatable using the formula that you see here below. With this one, we do have the input kind of being multiplied against the weight, to give us, that activation function. The neural networks, of course, build up in complexity, so we can have our input layers, then we have our hidden layer or layers. It could be multiple ones. And then, of course, we have an output layer that we have. The interesting thing about this is the choice of which hyperparameters we have has to be done manually. And that includes the type of activation function that we choose, the choice of architecture, how many layers we have in between the hidden ones, that is, and how big they are. The learning rate, the number of training epochs, or the amount of time it takes to go through all the material, and what features are presented at the input layer, and then how to regularize it to perform consistently. And I'm not really sure what the point of this slide is. When I looked at it at first, they have this, but it's not really a graphic; it's a video. So I sat there looking at it for a little while. What I would suggest is that you play this on your own. Let me see how long.
Today we are going to learn what neural networks are and how do they work. So, neural networks serve as the foundation for deep learning. They are loosely modeled after the neurons present in our brain. They try to solve problems by learning through vast amounts of data and examples. They are designed to recognize and find patterns in data. This helps them in time.
Right now, I'm pausing this video because if I'm not mistaken, this is the same exact video that we saw in the machine learning class. And this is something you can watch on your own. I don't need to do it for you. So please, if you want the reinforcement, please watch the video all the way through. But kind of the point here is, and this is kind of it's not laid out in the traditional layout that we're used to seeing, like in this slide here. But if you notice, we have these inputs, which are basically shapes of objects. It goes through the network, however that happens, and then we get to the output layer where we decide, is it an apple or not an apple, right? So that's an example of a classification example. Different types of activation functions that we use. There's a step function, and they show you the formulas for it and what it looks like when it's graphed on a Cartesian chart. I want you to notice that the step function is from 0 and above, right? So, we're basically just looking for it to trigger on, to trigger a 1 to activate it. With a signum function, we have both positive and negative values, and typically the positive value is the activator and the negative is off, and that's kind of like a computer sciencey kind of approach, right? In a sense. And then we have linear functions, which would plot on a chart and can go from negative to positive to whatever value that we have. There's also the ReLU function, if you remember, and that one is like basically flatlined until it hits a linear function. We have the sigmoid function, which introduces a curve shape from 0 to positive values, and then the hyperbolic tangent, which goes from negative curved shapes to positive curved shapes. But either way, whatever the mechanism is, they're all looking to trigger to true to get it to activate. And the point of it really is to identify the fact that you can use different types of mathematical functions and still trigger something to true. Here's another group activity, and this one I'm not going to assign as an assignment, but it says suppose f is the ReLU function, find z if z equals these values, and which one would trigger. And really the trick to this one is to look here at this chart, right? So if we throw z in here, if it's 0, right, if z is less than 0, it's basically not going to trigger. If it's greater than or equal to 0, it will trigger. So then therefore the answer to these is will trigger, will not trigger. You know, that's really what the group activity is. All right. Okay, so they asked the question here, why activation functions? There's input into the activation function where we have this given formula here, Wx plus B, where W is the weight of the cell, X is the input, and then there's a bias added to that. This value, if not restricted to a certain limit, can go very high in magnitude, which is kind of interesting. There's also the ability to add nonlinear formulas into the neural network. Of course, that adds to the processing time and everything, but that is absolutely feasible. All the neural networks consist of layers. We have the input layer, the output layer, and then we have the hidden layers in between. And, you know, we've covered a lot of this stuff, which is why I'm going through it so quickly. We can also, as we'll see with the TensorFlow website, which is part of our homework, we have the ability to change the learning rate. And basically what that does is it controls how much to change the model in response to the estimated error each time the model weights are updated. The value of the learning rate, if it's too small, could result in a long training process that could get stuck, right? So this is one of the problems with it. And a value of a learning rate too large may not obtain an optimal parameter value. So the point of it is you have to play with it a little bit to find the right level for the particular model. An epoch, and this is one of those terminology things, that it's defined as a single training iteration of all batches in both forward and back propagation. And it says the number of epochs you would use to train your network can be chosen by you. You don't have to pick some given amount, right? You can decide, and really you're looking at your output to make these decisions typically. The more number of epochs would show higher accuracy of the network. However, it also take a lot longer for the network to converge, right? In other words, to come to a conclusion, basically. There's also the loss function. It measures how well the network is performing. And it basically, it's looking at how many errors we're getting in the predictions. And the goal is to reduce the number of errors by tweaking things, basically, and adjusting them until we get, you know, an optimal approach. All right, let's look now at deep learning. Deep learning is basically a neural network where we have multiple hidden layers. I mean, that's the essential difference. Because of those additional hidden layers, we're adding much more mathematical complexity, more pathways, more processing time for all of it. When this is appropriate is basically when what we're trying to figure out is a lot more complex. You know, like when it might be really easy to see the difference between, let's say, an apple and a banana. But what if you have like a red apple and a green apple, and then you have like a pear, and I'm trying to think of a fruit that looks like an apple, but you know, there's some fruits that look really, really similar, and people can't kind of tell apart and figure out what kind they are. So they're saying here that it's beneficial then to use deep learning. The bigram neural network model predicts the next word. And this is something that we see in practice these days a lot, like when you're typing up an email, for example. This says the input is passed as a one-hot vector. The model will learn compressed continuous representations of words. This is part of our assignment, by the way, for this class, is to go to this website. And I'm not going to do this demo during the PowerPoint here as I'm lecturing, but when we have class, I will bring this up and we will tinker with this a lot. And in essence, try to help everybody with the homework. This is a tool that we've played with in the past, albeit briefly. I think we did it in the first course. I think we did it in the machine learning course as well. but this is the TensorFlow website, basically. It looks like this, and we can control how many neurons we have, the number of layers in between, and then we can start playing with all the different little things, and then we start to see the output, and it does create a visual of the output to organize the data so that we can see it. I think it's like amazing that they have this out there as a website, or you can just tinker it with it in the browser and you get results, and it's kind of like mind blowing in that regard. And basically, there's a preliminary task, and this is one of the things I hope to do during class tonight. And yes, I'm recording this before class, is to kind of play with these group activities. So I'm not really going to cover them here. And then ultimately, when you do the homework, which is based on TensorFlow, there's very specific things that you have to do. And then I want you to record your observations. Here's another group activity that we're going to do in class here tonight. And we're going to play with these tools. So once again, they're kind of giving us a primer on it. And I think what would be a lot more useful for us is when we do it live together in the classroom. And they give us a link. This is from an educational site. So they had some students code this. So I think that's pretty cool. And let's move on topic-wise so we can get through this material here. It says, now that we know the basics of some of the algorithms, let's look at their applications. All right, so this is where we start to delve back into the language models. Okay, why all that machine learning stuff? Because it does apply to natural language processing. And it indicates here they're crucial actually for natural language modeling. There's a bunch of them that we're already familiar with that we use on a day-to-day basis, and they've been around for a while now, right? So a lot of us use like Siri on our iPhones, or the Google Assistant on our Android phones, or maybe you have like an Amazon Echo or something like that, and you're talking to Alexa all the time. And I remember like the first time I saw one of those in action, I have a friend who is way into the Amazon platform, and he wired up his whole house with like smart devices. And he walks into a room, and he says, Alexa, turn on the toaster or something like that, right? And it works. And it was the very first time I saw it, I was like, wow, that's really, really cool that it understands them and it can trigger a function. So how does it learn basically like what the heck we're talking about? Like, how does it do that? Basically, a language model learns to predict the probability of a sequence of words, right? So here's an example. The cat sits there. There sits the cat, okay? Or their cat sits the, okay? That one doesn't make sense, right? Because of the placement of the word the. I mean, the cat sits there and their cat sits, their cat sits doesn't really make sense, right? That's not the normal order how we speak in English in terms of, our subjects and nouns and, all that stuff. The point of this is that we can train models by giving it large volumes of information that helps it to understand that the first approach is better or more common, right? That's how we do it in the English language. When we do language models, there's basically these two types. We have either statistical models, where we do things like n-grams and learn linguistic rules. And then there's neural language models where we use neural networks to predict the probability of words. Both approaches are used. All right, so now let's take a look at how these models operate. LLMs do go through two primary stages, pre-training and fine-tuning. The pre-training involves training the model on a big data set. So you get lots and lots of information. This basically utilizes unsupervised learning techniques to basically figure out what words follow, or filling in words that are blank by looking at really large data sets, basically. Mostly we train these large language models on text from the internet. So the more stuff that's out on the internet, the better. I think it's ironic that like how much of it is based on like Wikipedia, for example, or news articles, or that type of thing. But it can also be books and regular websites, people putting content out there. The point is it learns grammar, syntax, and semantics. There's a bunch of different ways to predict, what words are coming next, or what, models, focus on different types of techniques to figure out what, the sequence of the words is. After the models are trained, we fine tune the models on data sets that are specific to a task. So like if you were, let's say, in a coding world, you might give it coding syntax, which is different than like English syntax. Or if you're in medicine or law or something like that, you give it data sets that are, geared towards that. That's typically done with supervised learning models. So like things are labeled, right? So we understand like, okay, well, this is that, and this, this is a cat, this is a dog, that kind of thing. They also use techniques like gradient descent, back propagation to optimize the model's performance. So sometimes the data travels backwards, if you guys remember that. In context learning are where the large language models can figure out what you're doing without retraining. They're smart enough at some point to just kind of figure it out without having to go through a whole big giant set of data. And or they can kind of like just get a couple of examples and then so basically the point is, even though they weren't trained on that task, you can give them an example of like what you're trying to achieve, and then it figures it out and gives you something that you want. And I think that's a trick to prompting generative AIs, by the way, is to give it really good specifics, or here's an example of what I'm looking for, but can you please apply this to this other scenario? And the point obviously is, well, we don't need to retrain the model now because it already kind of knows how to do it. So now it says, now that we know the workings of LLMs, let's explore another category called discriminative language models and how they're different than generative language models. So the discriminative models divide the data space into classes by learning the boundaries. The models are used to discriminate between different classes and predict the probability of a certain class label given an input, right? They learn about the relationship between inputs and outputs. And some of the examples, right, are logistic regression, support vector machines, and neural networks all fall into that category. But I think really the point here is they look at different classes, right? This is, and they predict the probability of a certain label given an input. So like if and I'm thinking apples and oranges again, but if I use the word, feline, I realize that means cat. And if I use canine, I realize that means dog, right? And that type of thing, right? Where you're associating words together, kind of pre-labeled. All right. I'm letting you read these for yourself. And it says here, we're going to discuss a recipe for training large models. All right. This QR code here, and yes, you can pull this up on your phone if you wish, but if you look in the notes section down below in PowerPoint, and I don't know how you guys look at your PowerPoints, but if you're in this mode, you can kind of pull up from the bottom here and see the notes, or you can make the notes appear on the side or whatever. There is a case study that's pretty detailed on this website. And it gives you a lot of really good guidelines and stuff. I strongly suggest reading through this at your leisure, and I'm not going to go through it during class time. I find that pretty inefficient. So make sure you do read up on that. Now, the question that we have, and I was thinking about making this also an extra credit assignment, by the way, and I haven't quite done that yet as I record this video, but I might, is to read that case study and then respond to these questions and notice what the questions are. What are the key challenges associated with training large models? What training strategies do they use, and what techniques? And how does data pre-processing and augmentation contribute to this? and you provide examples, right? So I think that makes for a really good extra credit assignment. And I'll kind of weigh that a little bit. And an additional set of questions here. I'll let you read those on your own, and they just continue, right? So those are most likely going to end up as an extra credit assignment. All right. Next topic area here is working with n-grams for language modeling. And if you guys recall, we kind of talked about this already, including the formulas for it. But what they're looking at is basically this formula that, given the words that you already have in your document, what's the probability of seeing those words again? And then they set it up as a mathematical rule that you can process. And we can look at the context of the word. So it says, for an example, in the sentence, the child plays happily, we can predict the occurrence of happily by seeing the word plays. Happily plays kind of fits. Or seeing the word child, right? Child plays or plays child maybe isn't quite as common of a sequence, right? When we work with NLTK, we can work with these libraries, and notice how they have like bigrams and trigrams and all these different things. And that is something we've played with a little bit. So here's basically the Python examples. And once again, just keep in mind that it's relative to the task that we have in order to complete the work. They give examples for how to find the frequencies using those formulas that we're talking about. And they have an example of the code here, which is helpful. You can also look at the probabilities of words, and then they basically rank it numerically. And notice it's in the form of a dictionary, where like this is the key, like we're looking for Asia and how likely that is to happen. And basically what they're really doing here is you would get a list of the words that could follow many of, and the trailways, our, its, and notice how many of the is a very natural phrase, right? So that one gets a really high score, whereas many of trailways is not quite so common, so the score is much lower. Or many of its is higher because that's kind of pretty normal. They do have this other technique here called reinforcement learning from human feedback. And there's a bunch of different considerations for this. Now, I am going to pause here for just a moment and take a break, and I will come back and finish the recording. My dog is asking to go off.